Right, hello, and yeah, welcome to what is now part 6 of our Key Stage 4 look at waves. So, last lesson, lesson 5, we looked at the electromagnetic spectrum. And for that, we were actually looking at different types of waves. We looked at sound waves, seismic waves, as I said, the electromagnetic spectrum. What we're actually going to do today is start one of sort of 3 lessons inside of actually how waves react in different situations. So today we're going to be looking at reflection and something which is called refraction. Let's say this is lesson 6, so if there's anything else you don't say, you know, with amplitude, wavelength, frequency, things like that, the basics, you need to go back to the beginning. But as I say, we're going to go just straight in here with reflection and refraction. So what are these 2 things? So reflection, as I'm sure most of you know by now, you look in the mirror, you see your reflection. So what it is when a wave bounces off an object. So when a wave can actually hit an object and rebound straight back off it, that is, well, the rebound is the reflection. The refraction is when the path of a wave is changed as it passes through an object. So, you know, as light will pass through a lens or as it actually goes through some glass, is how it's actually bent as it goes through. It doesn't actually just travel straight through. And there's various reasons for that, of which we will get to into the second part of this lesson. But for now, we're just going to focus on reflection. So, reflection, how it works. So obviously, as I said, you know, what happens is the light waves are coming down, they're hitting a reflective object, which is actually then bouncing those rays back off. So there's a couple of rules here. There's 3 general rules for reflection, and this is the first one. First rule is that the angle of incidence, so the angle of what's called the angle of incidence, is actually the angle of which the light ray hits our object. So in this case, a mirror. To keep things nice and simple, our angle of incidence is the angle of which the wave actually hits the mirror. Now, as it's reflected, nice and easy, it's called the angle of reflection. Now, these 2 angles are exactly the same, and what they're actually taken from, they're taken from a line which is called the line of normality, or the normal line, which is at 90 degrees to our reflective surface. So this angle here, our angle of incidence, will be exactly the same in degrees as our angle of reflection. And that is our first rule of reflection. Now, obviously not all surfaces are flat, as our nice flat mirror is here. So obviously the angles may not necessarily come off the same way. So what we've actually got here, this is a picture of some light rays going onto a convex mirror. So as you can see, as the light rays hit this convex mirror, so it's actually bent outwards like that, you can see because the angle of the surface that it's hitting is curved, the angle of the light as it goes off it is also curved away as well. Now this works the other way around as well. If the mirror is convex, so it's curved around like this. So this is the edge of our mirror here. If you ignore this bit is actually the reflection in the actual mirror, but this is where the light beams are actually passing off. So as the curve of this mirror is here, you've actually got the light beams are bouncing back in towards each other. So obviously depending on the surface that it's reflecting from will depend on how it actually reflects, but don't forget our rule number 1, that if it's reflecting off a flat surface, the angle of incidence will be exactly the same as the angle of reflection. So that is our first rule of reflection. Now, the second and third rules of reflection are to do with how we actually see images in a mirror. Now, our brain's a bit stupid, really. Our brain automatically thinks that light rays can only travel in straight lines. It doesn't really understand the concept of reflection. So what you can see here is this is something which, as we can see up in the top corner here, is called a virtual image. So when you actually stare into a mirror, your eye still thinks that it's focusing actually through the mirror, and the image that it's seeing is behind the mirror, where obviously in this case the sun is actually behind where we're looking. But because our brain doesn't get the idea that the light can be bent or can be reflected, we just see it as a straight line. So we see this thing which is called the virtual image. Now, the virtual image that you see in a mirror, the distance that you perceive it to be behind the mirror is exactly the same as the actual distance that the object is from the mirror as well. And that's rule number 2. So the distance from the object to the mirror is the same as the distance from the mirror to the virtual image that you're seeing. So this image itself doesn't actually exist. It's just because our eye and our brain can't get the idea that the light is bouncing. It just thinks that light can only travel in a straight line. So we see this virtual image. Now, the third and final rule of reflection is that this virtual image that you will see will be exactly the same size as the actual object as well. So both the object and the virtual image will be the same size. So that is rules number 2 and 3. So as I said, there are 3 general rules of reflection. Rule number 1 is that on a flat reflective surface, the angle of incidence is equal to the angle of reflection. As I said, remember, as long as it's on a flat surface, if the surface is bent, then it's different. But if the surface is flat, then the angle of incidence is the same as the angle of reflection. Rule number 2, which is the distance from the object to the mirror, is equal to the distance of the image behind the mirror. So that basically means that the object distance to the mirror is the same as the distance from the mirror to our virtual image that we have. And our third and final rule is our object and image are the same size. The only difference is that the image is actually laterally inverted, so it's actually upside down and the wrong way round. Sorry, the wrong way round, not upside down, it's the wrong way round. So that means that when you look in the mirror, if we had something else that wasn't the sun, you would see that it'd actually be the wrong way round. So that's why whenever you look in a mirror, you see, I don't know, if you're in a car and you look in the mirror and you see that the numbers are backwards, or if you've ever written something and held it up to a mirror and you see that the word is backwards, that is why. It's because of the reflection, the virtual image is always flipped, so it's backwards. But just don't remember that the object, the actual object or the writing will still be the same size, it's just that it's turned the other way round. Okay, so that's our 3 rules of reflection and how reflection works. So now we're going to move on to refraction. As I said at the beginning, this is when the path of a wave is changed as it passes through an object. Now, if you haven't really come across this before, it's probably going to be easier to explain. Now, this is a pretty dark picture, but hopefully you'll be able to see that we've actually got a light coming through, a light beam coming across here, and what we've got here is just a glass block. So what's actually happening is that the light is still coming out of this side here, but as you can see, it's actually not straight. There's actually an angle to the way that the light's coming out. This angle that's created here is what's called refraction. It's the bending of the path of the light as it actually goes through. Now, there's several reasons for this. What I need to do is obviously get rid of these lines that I've just drawn on here. Now this is the diagram of obviously the picture that we've just seen. Is that as our ray comes in, again creating that incident angle here, which we have in reflection. In refraction, we're talking about, instead of it reflecting back off the surface, we're talking about it actually going through our object. Now, as I said, our incident angle here is different to what is called our refracted angle as it goes through the material. Now, the reason for this is that light in air travels at the speed of light, surprisingly enough, which is around about 300 million meters per second. Now, when it changes from air into a more denser material, so in this case we'll call it glass or perspex, it's a medium change. Remember we were talking about mediums, about how waves travel and how they need, some of them need mediums in order to travel. Well, the thing is that once a light ray goes from one medium to another, obviously that medium, this medium in this case here, is denser, so it's actually going to be harder for it to travel through that medium because it's that much denser. So then what actually happens is the wave starts to slow down. And as it actually reaches the other side and comes back into the air again, it's then releasing back into that lower density medium so it can speed back up again to its normal speed of light. Now the only time that this refraction angle doesn't work is when the incident angle is 0. So you'll find if our ray was coming straight in along our normal line, or our line of normality, then you would find again it would go straight through, because although it would travel slower, there is no angular movement for it to actually change. But as soon as there is an angle introduced, then it will actually start to either, as it slows down, it will bend towards what is called the line of normality. So why does that happen? Well, as we said, it changes through, it starts to slow down because of this change in medium. Now, if you think of, obviously we know that light waves are very, very, very thin, but if we take a slightly larger view of our light wave, as it travels in here, the first edge that it actually touches the medium, it starts to immediately slow down on this side here. And what you'll find, if you've ever had the pleasure of doing a small experiment in school, where you've had a few of you hand in hand in a line, and you start to walk around in a circle, you'll realise that the people on the outside are having to walk much faster than the person that's on the inside. And this is exactly what happens. As they start walking faster and faster on the outside, and you're still in the middle, you can leave your left foot just on the floor where it is, whereas they're obviously having to run round. This is exactly what's happening here, is that because it stops here, it starts to slow down, but ours still on the outside is still travelling a lot faster. So this actually means that once it exists, it actually starts to bend as it goes into this glass, and this bending is what's called refraction. So you try that, if you get sort of 5 of you, just hold hands at arm length, and have the one person on the inside just to stand still and start moving around, and then just automatically start moving around into a circle. You'll find the people on the outside are having to move a lot faster than you are standing on the inside. And that's exactly how refraction works. Alternatively, you can try it with a pencil on the table. Just push it gradually at the same time with both hands, and you'll see that it stays straight. Start pushing faster with your outsider hand, and you'll find that obviously that it starts to turn. And that's exactly how refraction works. So, with water, sometimes when you put a straw in your drink, you can see it from above, you think it's still going straight, but then you look from the side and it's bent. That's exactly, again, that's refraction again. That's just refraction through a different medium. So instead of it being through glass here, instead of it being through glass, it's through water, exactly like it is with this ruler. You know that ruler is straight, but because of the way that you're looking at it and the way that the light is refracting through the water, it looks like it's bent. So again, exactly how does that work? So here we go, we've got Captain Ahab trying to catch Nemo here. I know it's a little bit harsh, I do apologise, but it's just the way it goes. Now, when you look into the water, you would again see this ghost image, or this virtual image, because your brain can't work out the fact that the light is bending when it hits the water. So I mean, at this particular point, Nemo's laughing, he's well away, because he knows that Ahab's not going to get anywhere near him. Because Ahab doesn't know that the light rays are bending as it hits the water, so he still thinks that Nemo's over here, when obviously he's here. And again, this is just to do with, as it hits the water, the light rays are slowing down and they're bending round, but our brain can't concept that, so you still see this virtual image. It's exactly the same as with the reflection in the mirror. You still think that the image is actually behind the mirror, whereas obviously it's being reflected back. So that's how this virtual image is created, and it's all to do with refraction, and our brain's not being able to grasp the concept of light rays bending as it hits them through a different medium. So sound waves. Now we know sound waves work slightly different to light waves. We know that they're longitudinal waves instead of transverse ones, so they work on vibrations. So what actually happens with sound waves is that in the air, they travel relatively slowly because they rely on vibrations in between matter, or in between the medium. With air, it's obviously not very compressed, so it doesn't travel as well. But when, say for here, for example, we've got a door. The door is made of much more compressed material. It's made of the wood, so it can actually vibrate through that much easier. So therefore, it actually speeds up. So it adheres to all the same rules as light refraction, apart from the fact instead of slowing down when it goes into a denser material, it actually speeds up. So as we have our line of normality here again, through the middle, and what we'd expect if it was if it was refracting light, is that obviously it would slow down. So we would expect that our light ray would actually bend towards the line of normality. But as you can see, with sound, as it comes in here, it actually bends away from the line of normality. So that shows that it's actually speeding up, it's actually getting faster as it travels through the door. And that's exactly the reason why I said this, because the door is made of more compressed material. It's a higher, so the vibration can travel through it faster because the molecules are all closer together, so the vibration just travels that much faster, so it actually speeds up. And then when it reaches back to the air again, it actually starts to slow down and goes back to its slower speed. So as I said, sound does also refract. That's why you can, often hear people in another room, because it goes through a doorway, it can vibrate through a door. But it works exactly the same way as light refraction, except that as it goes into a medium that is more dense, it actually speeds up instead of slowing down. Okay. Sorry. So that was our look at reflection and refraction. So yeah, we've looked at the three main rules of reflection. We've looked at how virtual images are created. We've also looked at refraction of light waves and refraction of sound waves. Yep, so that's it for today's lesson. The next lesson we're going to be looking at something called dispersion and total internal reflection. Those are both quite interesting things. Total internal reflection actually has a lot of uses in the modern world. Dispersion is actually just quite good fun, you actually get the chance to do it. So yeah, that's the end of today's lesson. So my name's Ian McDowell, I'm a student from University. Thank you.